Welcome to the Basics of Electronics lecture. So last time with robotics we kind of got a general large overview from the fact that, well, dealing with robotics, there's more than just the software side. You have the AI side, but you have the physical components and everything else you need to deal with. Now for this course, I'm starting off by concentrating first on the physical components, and then working our way up to more what can we start doing when we combine things together, and then allowing you to branch off in the future if you want into things that maybe incorporate more stuff like AI. But again, that's a whole field on itself. So before going further, I want to deal with what is the basics of electronics that we need for this course. And we'll be adding a little bit more in as we go through future lectures and start working with more controllers. But this is what we can do in the very beginning. So I'll shrink myself down and we will start. So if you remember from last time, we talked about the 5 basic physical components of a robot, at least as they're being defined in this course. So again, your sensors for taking the electronic information in from the external world, your effectors to make some kind of change, your actuators, which are basically just effectors, but they are specifically used for moving the robot around in some way. You have the controllers, which act as the actual brain, and of course, and you have some kind of power supply. And all of these are physical components that are built up of electronics, and you have to connect them together to get everything working. So we had this image from last time, again, of a basic idea. And this is, again, more of a humanoid robot, but just something to visualize. The fact that you have the sensors, and you can see even here that internally it's showing connectors and stuff in between. Being this lines is that, well, we need to connect everything together. We need to have some kind of power source. All of these things are electronics, but built upon circuitry, resistors, capacitors, and everything else, and chips. And so if we're going to start building things, we're going to have to know, well, how do we connect these things up? What things affect stuff with the power and current and electricity. And so that's the focus of these notes, is to give you that beginning point for some terminology to talk about power, current, and circuits, some basic components that we're starting with and getting terminology down, and physical components. And just an understanding of, okay, from the ground up, where are we starting with the physical components of the actual robot before we get into some more of the software development, which will be coming in future lectures. So, as always, as I've mentioned in the previous ones, I like to kind of do things in couple parts. Is that I have these videos which give a general overview of what I'm going to actually cover, and also add some extra information to it and give you a chance to hear what someone else is actually saying. So we have 2 videos that I'll be going through in the beginning, and then the rest of these notes that I'll be talking.
Hey there guys, Paul here from theengineeringmindset.com. In this video, we are going to be looking at how electricity works. Now this is pretty essential knowledge for any engineer, so we'll run through the basic parts of what you need to know. So let's start at the very basics, and for that we need to take a look at the atom. Everything, including you, is made from atoms. All the materials we use are made from atoms. The materials are just different because the construction of their atoms are slightly different. The atoms are made from 3 particles, 2 of which are found inside the nucleus, and the third particle sits outside this. At the center of the atom we have the nucleus. Inside the nucleus we have the neutrons, which have no charge, and we also have the protons, which are positively charged. The neutrons and the protons are much heavier than the electrons, so these will stay within the nucleus. Surrounding the nucleus are different layers of orbital shells. These are like flight paths for the electrons. The electrons flow along these flight paths much like a satellite orbits our planet, except that the electrons travel at almost the speed of light. The electrons are negatively charged, and they are attracted to the positive charge of the protons. The electrons orbit around the nucleus in these orbital shells, and there are a set number of how many electrons can be in any one orbital shell. The number of protons, neutrons, and electron an atom has tells us which material it is. Atoms hold on to their electrons very tightly, but some materials will hold on to them more tightly than others. The outermost shell is known as the valence shell, and in this shell some materials have loosely bound electrons which can flow to other atoms. Atoms which can pass electrons are called conductors, and most metals are conductors. On the other hand, atoms which do not have free electrons and so they can't pass electrons between other atoms are known as insulators, and these are things like glass and rubber. Now we can combine these materials to safely use electricity by having the conductor in the center, which allows electrons to move, but surround this with an insulator to restrict where they can flow to, i.e. not into us, which keeps us safe. If we look inside a slice of copper cable at the free electrons surrounding the nucleus of the copper atom, you'll see that the free electrons are able to move to other atoms, but this happens randomly in any direction. If we then connect the slice of copper cable to a closed circuit with a power source, such as a battery, then the voltage will force the electrons to move, and these will then all flow in the same direction to try and get back to the other terminal of the battery. When I say circuit, this just means the route which electrons can flow along between the two terminals, the positive and the negative, of a power source. So we can add things into their path like light bulbs, and this means that the electrons will have to pass through this in order to get to the other terminal. And so we can use this to create things such as light. The circuit can even be open or closed. In a closed circuit, that means the electrons can flow around, and in an open circuit, this means that the electrons are not able to flow. Voltage is a pushing force of electrons within a circuit. It's like pressure in a water pipe. The more pressure you have, the more water can flow. The more voltage you have, the more electrons can flow. But what does a volt mean? Well, a volt is a joule per coulomb. And a joule is a measurement of energy or work, and a coulomb is a group of flowing electrons. We'll have a look at what a coulomb is in just a second though. So a 9-volt battery can provide 9 joules of energy in the form of work or heat per group of electrons that flow from one side of the battery to the other. In this case, the current of electrons flow from one side of the battery through the LED light bulb, which produces light, and then the electrons flow to the other side of the battery. Therefore, 9 joules of light and heat is produced by the light bulb. Current is the flow of electrons. When a circuit is closed, it means electrons can flow, and when the circuit is open, no electrons will flow. We can measure the flow of electrons just like you can measure the flow of water through a pipe. To measure the flow of electrons, we use the unit of amp. 1 amp means 1 coulomb per second, and 1 coulomb is a group of electrons. The group is incredibly large and is approximately 6,242,000,000,000,000,000 electrons, and that has to pass in 1 second for it to equal 1 amp. That's why electrons are grouped together and just called amps to make it easier for engineers. Resistance is a restriction to the flow of electrons in a circuit. The wire which carries the electrons will naturally have some resistance. The longer the wire, the greater the resistance. The thicker the wire, the lower the resistance. Resistance to the flow of electrons is different for each material, and the temperature of the material can also change the resistance to the flow of electrons. Electrical circuits use specially designed components known as resistors to purposely restrict the flow of electrons. This is either to protect other components from too many electrons flowing through it, or it can also be used to create light and heat, such as in an incandescent light bulb. Resistance occurs when electrons collide with atoms. The amount of collisions is different from one material to another. Copper has a very low collision rate, but other materials such as iron will have much more collisions. When collisions occur, the atoms generate heat, and at a certain temperature the material will then start to produce light as well as heat, which is how the incandescent lamps work. When a wire is wrapped in a coil, it will generate a magnetic field as the current passes through it. The cable will naturally create an electromagnetic field by itself, it's just intensified by the coil. By wrapping it in a coil, the magnetic field becomes so strong that the magnetic field starts to actually affect the electrons within the wire. But we'll look at why this occurs in a future, more advanced video. We can increase the strength of the magnetic field simply by wrapping the coils around an iron core. We can also increase the number of turns within the coils, and also we can increase the amount of current passing through the circuit. Now this is how electromagnets work, and it's also the basis of how induction motors work. If you want to learn more about induction motors, we've already covered this in another video already, just see the link on screen now. Now when a magnetic field passes across a coil of wire, it will induce a voltage in that wire caused by an induced electromotive force which is pushing the electrons in a certain direction. If the wire is connected in a circuit, then this electromotive force will cause a current to flow. This is the basis of how AC generators work, and the electricity at your wall sockets within your home is produced in a very similar way. Transformer. Now we can combine all of the aspects together that we've just covered, and when we do so we'll see that we can use one coil to generate electricity, and then we can place two other coils in very close proximity to each other but not touching, and this will create a transformer. The transformer will induce a voltage from the first or the primary coil over into the secondary coil, and this will force electrons to flow if the coil in the secondary side has a closed circuit. Now what's important about the transformer is that we can increase or decrease the voltage between the primary and the secondary coils simply by changing the amount of coils on either side. Again, this is a subject all by itself, so we'll cover this in a more advanced video later on. Now something else which I just want to briefly mention is the capacitor. So a capacitor forces positive and negative charges to separate across two plates when it is connected to a power supply. This causes a build-up or store of electrons within an electric field. When the power supply is cut or interrupted, these charges will then be released, flow up and meet again. This provides a power source but only for a few seconds until the charges have paired back up again. It's slightly similar to a battery, but capacitors are very common and they're in almost every single circuit board. We'll cover this obviously in more detail in a future video, just be aware of these. So the last part I want to cover in this video is that there are two types of current electricity, that being alternating current or AC and then direct current or DC. Alternating current simply means that the current flows backwards and forwards in a circuit as the terminals are constantly reversed. This is a bit like the tide of the sea. It goes in and out, in and out, in and out, so that it's reversing constantly. Now alternating current is the most common source of power, and the plug sockets in your homes and your buildings and schools and workplace, etc. These will all be providing alternating current, AC. Now on the other hand, we've got direct current or DC, and that simply means that the current flows directly in only one direction. It does not alternate. This is what's provided from batteries, and almost all your handheld devices are from this as well. So we can convert AC to DC and vice versa using power electronics. And this is how we charge and power small devices. And it's also how solar panels can be used to power our homes, because solar panels produce DC power and our homes need AC power. So we have to convert this for it to be usable. So both AC and DC have pros and cons to it, but for sure we'll look at this in another later video. It's a bit more advanced, and there's also quite an interesting history behind.
Okay, that last part went into more advanced stuff, but we're starting the very basics of understanding, well, everything is atoms, and you have these electrons, and they're moving through that path, and that some materials allow electrons to move easier than others. So you have conductive material, things like you're used to, like pieces of other metal, versus things like plastic, an example of things that don't conduct well and will stop it. And you have to be careful, like our own bodies ourselves will actually allow stuff to be conductive like electricity, so even you touching circuits can have an effect, and you have to be careful about what you do. And the fact that you have these circuits and flowing. Okay, the next one is more about current, so going beyond just the basics of electricity, but understanding current, which is basically trying to use this energy to harness to do work for us, and that flow of electronics from one end to the other and what happens.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be discussing electrical current. We'll be looking at what is current, the different types of current, how to check the ratings of your electrical devices, as well as how we use safety features to save you from being electrocuted. Current is the flow of electrons in a circuit. To use electricity, we need electrons to flow in the same direction around a circuit. We usually use copper cables to form the circuit because the atoms that make copper have a loosely bound electron in their outermost or valence shell, which is free to move around inside the metal. This free electron is very easy to move, which is why copper is so popular. It's so easy to move that it will naturally just move to other copper atoms by itself, but this occurs randomly in any and all directions, which isn't useful for us. For us to make use of this, we need lots of electrons to flow in the same direction along the circuit. We can then place things like lamps in the way of these electrons so that they flow through it and then they generate light and heat, etc. To do this, we need to force the electrons to move, and we can do that by applying a voltage. Voltage is the pushing force. It's like pressure in a water pipe. The more pressure we have, the more water can flow. The more voltage we have, the more electrons can flow. We've covered the basics of voltage in detail in our previous video. Do check that out, links in the video description down below. So we need a lot of electrons to flow along a circuit and through our lamps to get them to shine brightly. However, the cable and lamps can only handle a certain amount of electrons passing through them. Just like a pipe is rated to handle a certain amount of water passing through it, or a certain pressure. If it exceeds this, then the pipe will burst. Likewise, if too many electrons pass through the cable or the lamp, then they will just burst or burn out. We refer to the flow of electrons as current, and we measure this in the unit of amperes, although you'll usually just hear people say amps. This is represented with a capital A. For example, this fuse has a 3 and a capital A, which means it's rated to 3 amps of current. We'll look at how we use fuses later on in this video. If you look on the plugs of your electrical devices, you should find labels from the manufacturers which tell you what the product is designed to handle. For example, this laptop charger tells us that for the device to work, it needs an input of between 100 and 240 volts and 1.5 amps of AC or alternating current. The charger will then convert this to give an output of 19.5 volts and 3.3 amps of DC or direct current. AC and DC are different types of electricity. The plugs in your homes will provide AC or alternating current. In this type, the electrons do not flow in a continuous loop, they instead alternate between moving backwards and forwards, just like the tide of the sea. Your electrical devices like laptops and mobile phones will use DC electricity or direct current. In this type, the electrons do flow in only one direction, much like the flow of water in a river. We transport electricity from the power stations in AC alternating current and send this to our cities and homes. We use AC here because it can be transported very efficiently and over much greater distances than if we were to use DC direct current. We can also very easily increase or decrease the voltage using simple transformers. We've covered how transformers work in our previous videos, links down below for that, do check them out. We mostly use DC direct current in the circuit boards of small electronic devices like laptops, mobile phones and televisions. That's because DC is easier to control and allows circuits to be smaller and more compact. Many appliances will use a combination of AC and DC. For example, a washing machine will use AC for the induction motor, which is used to spin the tub with the clothes in. But the circuit board, which controls the settings, the lights, the timers, as well as how fast the motor spins, will use DC power. We can convert AC to DC using an inverter. This is extremely common in electronics. We've covered how inverters work previously, links down below if you want to watch and learn about that also. People often refer to a river or the tide of a sea as having a strong current. It's very similar to electricity. A river with a lot of fast-flowing water is said to have a strong current. The same with electricity. A cable with a lot of electrons flowing through it has a high current. A river is able to handle a certain amount of water flowing through it, but if more water enters than the river can handle, then the river will burst its banks. The same with electricity. The cable will burst and burn out. Therefore, manufacturers need to be able to test cables and lamps to find out how much current they can handle. We also want to be able to see how much current is flowing through our circuits, as well as being able to calculate this. We can measure this using an ammeter, and we measure the flow of current in the circuit using the units of amps. So what is an amp? 1 amp is equal to 1 coulomb, and 1 coulomb is equal to approximately 6,242 quadrillion electrons per second. What does that mean? Another way to look at this is that to power this 1.5 watt lamp with a 1.5 volt battery, approximately 6,242 quadrillion electrons need to flow from the battery and through the lamp every second for the lamp to stay on. If we reduce the voltage, then less electrons will move and the lamp will become dimmer. If we increase the voltage, then more electrons will flow and eventually the lamp will not be able to cope, so it will burst or burn out. So to measure the current in a circuit, we need to connect an ammeter in series so that the current flows through it. Think of it like a water meter. The water needs to flow through the water meter for us to know how much water is flowing in the pipe. Likewise, we need the electrons to flow through our ammeter so that we know how much electricity is flowing in our circuit. Instead of using an ammeter, we're going to use a multimeter, as we can do a lot more with this device. I'll leave some links down in the video description where you can pick up a good multimeter cheaply. I highly encourage you to get one of these for your toolkit. They're pretty cheap and are very useful. If we connect a lamp to a battery in series, then we can measure the current using a multimeter by connecting it in series. If we connect this 1.5 volt battery and this lamp, which has a resistance of 1 ohm, then we get a current reading of 1.5 amps, which means 9,636 quadrillion electrons are flowing through the lamp every second. Because it's in series, all the electrons in the circuit are flowing along the same path. So that means we can move the multimeter to here and we get the same reading. If we add another lamp to the circuit, connected again in series, the lamp also has a resistance of 1 ohm, then we are adding more resistance to the circuit, so the electrons are slowed down. In this case, we get a reading of 0.75 amps, which means 4,818 quadrillion electrons are flowing per second. This is in series, so again, we can move the multimeter and we get the same reading. If we now connect the circuit with 2 lamps in parallel, both with a resistance of 1 ohm, and connect this to a battery of 1.5 volts, then in the main wire to and from the battery, we get 3 amps. But on the branch of each lamp, we get 1.5 amps. That's because the path of the electrons has split, so the electrons are shared with some flowing through lamp A and some flowing through lamp B. In this example, both lamps have an equal resistance, so the current is split equally. But if the lamps are of different resistance, then the current is split unequally. For example, if lamp A has a resistance of 1 ohm and lamp B has a resistance of 3 ohms, then in the main wire we get an amp reading of 2 amps. In the branch for lamp A, we get 1.5 amps, and in the branch for lamp B, we get 0.5 amps. As you can see, lamp B is dimmer because there is a higher resistance, so less electrons can flow through it. In both cases, the amps in the branches will add up and are equal to the total current flowing in the main wire to and from the battery. Now I mentioned that lamp B was dimmer because the resistance was higher. If you remember, I also said that cables and lamps etc. are only rated to handle a certain amount of current. If it exceeds this, then they can burn out. So to restrict the amount of current that can flow, we can add resistors into the circuit or into part of the circuit. These act like speed bumps and slow the electrons down. Resistors are like putting a bend into a garden hose. The kink adds resistance to the flow of water, which reduces the amount of water that can flow out of the hose. Similarly, we can add resistors to the circuit and it slows down the electrons. For example, this LED is rated at 25 milliamps and 3.3 volts, but our battery is rated at 9 volts. So if we were to connect the LED to the battery, it will just burn out because it can't handle that much voltage and current. So to stop the battery from burning out, we need to place a resistor into the circuit. In this case, we'll use a 270 ohm resistor to bring the voltage and current down to a safe level for the LED. If you want to see how much current is flowing through your electrical devices at home, then you can use one of these cheap energy meters. You simply plug your appliances into it and it'll measure the voltage, amps, watts, power factor, etc. and you can then even calculate how much it costs to use the appliance. I recommend you have one of these. They're a great little device for your toolkit. I'll leave some links down below for where you can get a good one very cheaply. So we saw earlier that we can use resistors to reduce the amount of current flowing in the circuit and protect our devices. Another thing we can use is a fuse. Fuses, in a basic sense, have a thin piece of wire inside them which is rated to handle a certain amount of current flowing through them. In this case, this one is rated to handle 3 amp or 19 quintillion 272 quadrillion electrons per second. The fuse acts as a weak point and is very cheap to replace. So if too much current flows in the circuit, it will burn out and open to break the circuit and protect the more expensive electrical components. You can find these mounted on circuit boards, and you can also find these built into some plugs. For example, this plug from the UK has a fuse built into it to protect the electrical device. Another device we use, and you've probably seen these in your homes, this is the circuit breaker. It's essentially a switch that will automatically open to break the circuit if it detects too much current or too many electrons flowing through it. It's rated to handle a certain amount of electrons flowing through it per second, but it measures this using heat or an electromagnetic field to detect and act on if too many electrons are passing through it. If it exceeds this, then it will open to break the circuit. If, for example, we slowly add load to a circuit, then the bimetallic plate will detect this slow rising current because the current causes it to heat up. As it approaches the design rating, it will break the circuit to cut the power and protect the cables and devices. The load can then be reduced and the circuit breaker reset, unlike a fuse. Another extremely important function is if, for example, you touch a live component and receive an electrical shock. There will be a sudden surge in current and the circuit breaker can detect this and cut the power almost instantly to stop you being electrocuted and save your life.
Okay, so now we got more of an explanation beyond just basic electricity into actual current that flow. That if we have a power source that has some level of volts being the pressure at which it's going to help push electrons through, we then have current being that flow, and we start talking about amps as a measure of that rate of flow. And as it goes through different materials, that if it's too high, it could cause a wire to burst, it could cause components to actually break, and you need to be careful about that, because then maybe you start adding resistors in to limit the flow, and so it doesn't damage that actual device, but allows it to do its work, so the components, the lights, motors, what forth. You also then have to worry about if the power is too high, it's just going to burn out the wires, so you have to be careful what you're connecting, and not just connect anything randomly. What are its tolerances? Like thin wires to larger wires have a big difference for what you can do. Also, what you can run. If it's a motor that's too high, well, not enough volts and not enough amps, nothing is going to actually happen. It's going to be too low. Or if hooking things up like motors could have an issue overall on the actual circuit. So you need to take those things into account.
Okay, that's it for this.
Okay, so starting as usual over, like, those videos again were just a general introduction to give you a feel. You don't need to memorize and know everything from them perfectly. I want it to be like, hey, here's what will stick from those videos first, and then what I'm adding into it by going through the rest of these notes. So, electrical basics. The world of electricity, we're dealing with atoms and those movement of electrons. And we need to start with understanding first the idea of, again, being voltage, current, and resistance, adding into all. And these are the basic building blocks of everything that you will use with electricity. Now, electrical charge itself, electricity, again, is the movement of electrons, as we've seen. That some electrons allow jumping, moving between and giving that flow. And these electrons create charge, which then can be harnessed and used for work. So this being with your components. So if this is an LED or light, then it's going to emit light and you'll see it. Or if it's a motor, this motor is going to actually move, or whatever other components you're working with. If this is a sensor, which is usually built up of other materials, well, then that will power so that sensor can do information, then send a signal along. So basically from this, again, we have voltage. So from electrical charge, the three basic principles can be explained by using electrons, or more specifically that they create a voltage, and this is the difference in charge between 2 points. So physical points, you're thinking that from point A to point B, well, that is voltage, that measurement that you're actually working with, and it's referred to as volts. You have current, which is the rate of flow from points, and you have resistance, which is material that has tendency to slow the flow of electrons. So taking from 1 amp and lowering it to another amp, being that measurement of current. So when we talk about these values, we are actually describing movement of charge and thus the behavior of electrons. So when we talk about voltage, current, and resistance, we're really talking about the movement of those electrons as they move through different devices. As we add components into the actual circuit, those will use up some of the actual charge and act like a resistance. So slow and use them up, and you get that transfer change of energy. to deal with, and we have to worry about, well, what happens when we connect too many things or too few things, or what's going on and how we connect them. Now, a circuit is a closed loop that allows charge to move from one place to another. So this means that you have some kind of power source, and then you're taking from one point some kind of medium that allows the conductive nature of like electrons to move, and tying that to other components, and then coming back. So there's this complete cycle that you start from that beginning power source, and you have the movement, and to get the voltage there has to be something that's drawing it across, which is from the start of the power source and back to the actual power source and through other mediums. Components in the circuit allow us then to control the charge and use it to do work. What we want it all, and like the building blocks of our entire robot and these physical components we talked about earlier. So voltage. It's the amount of potential energy between 2 points. One point has a charge, more charge than another. So it's kind of like a billet. This has more pressure versus lower pressure. This difference in charge between the 2 points is called voltage, and it's measured in a unit called volts. And you're used to that when you've seen batteries, things like that, like a 1.5 volt battery or a 9 volt battery or so forth. But all of our electronic components that are working with this direct current and one direct flow of electrons like have requirements of a specific amount of voltage that's required to run that device. Too low, nothing happens. Too high, blows up. So how do you manage how many things you do, and how many, like the more things I plug in, well, maybe I need more power, I need more amps, and the actual flow to deal with this. So an analogy that's used a lot, and just take this as an analogy. There's way more, and you go deeper into the science of it. But if we go for a basic analogy, which is good enough for this course, and think about water flowing through hoses and kind of movement, we go to the water analogy. So for voltage, we want to think about this as being a water tank. So in describing current, in this analogy, charge is represented by the amount of water that's in that tank. Voltage is represented by the water pressure. So usually when you have tanks, you have water coming down, the weight of that is causing pressure from the tank and through whatever connected hose, which will then allow for flow. And current represents the actual water flowing through from that tank through the hoses. So, when we have a tank that's going above and you have water, and there's going to be weight, the gravity is pushing stuff down. And if there's a hose with the valve open, it's going to want to go down and flow through that. So the pressure from above pushing something down. So going from a higher to lower to start flowing through. So for this analogy, we want to remember that water equals the actual charge, being the flow is that pressure that you need. Pressure is the actual voltage you're working with, so not enough pressure, things aren't going to move. Lots of pressure, maybe too fast. And the actual flow, or the rate of flow, is the current, so that'd be the electrons moving through the circuit itself. Now, what we want to think of this tank in the end, if we're going with this analogy with the voltage, in a circuitry, the tank would be your battery that you're plugging in, so whatever power source you have. A lot of times for other devices moving around, we'll have 1.5 volt batteries or 9 volt batteries or whatever, or you have some other kind of actual power source, something that is holding an amount of energy and it wants to to use later on to release it. If we drain our tank a certain amount, the pressure created at the end of the hose goes down. So remember this, it's like even a battery, when it gets weaker to the bottom, well, how much pressure you actually have been going through, so that actual voltage changes. And we can think of this decrease in voltage like when a flashlight gets dimmer and batteries run down. So something's dying down in a flashlight, the light's getting dimmer, it's not working, you maybe need new batteries, you need to recharge it, and you need to refill up that actual tank to build up that charge and actual voltage, because it only has a certain amount in the actual beginning. There's also a decrease in the amount of water that will flow through the hose, and less pressure means there's less water is flowing, which brings us to current, and that's this flow. So it's more like, well, we need a tank, we need some kind of pressure source to bring the voltage, so we need a battery in the beginning that's fully charged, but as it's running, it's going to get discharged, and as you reach the bottom of that discharge, well, problems could occur. Now, if we're plugged in for direct power into the wall, then we're not really worrying about that. We have AC current that's being converted into DC current at a continuous rate. So as long as there's a constant stream coming in from the AC source or whatever other source, we're fine, we don't worry. It's like a constantly replenishing actual tank. But if we're dealing with separated battery sources, well, we have to worry about that. At some point in time while things are running, the battery is going to run out, and whatever robot we have is just going to shut down, and maybe even just before it shuts down, it's going to start doing things really weirdly. So just like us running out of energy and not thinking properly later in the day if we haven't had enough food or we worked out too much or whatever else is going on. But that's the voltage part again. So that tank and the pressure inside of that, so the water levels and what's going to flow through it, you can think of that as being that voltage. We need that as that first pressure to move things through. But then now as things are moving through, we have flow of the actual electrons or water in this analogy. And we refer to that as current, and we measure that in amps. So we can think about the amount of water flowing through the hose in that tank as current. The higher the pressure, the higher the flow, and vice versa. So we need to worry about those two things. That's the connection between voltage and actual amps. Higher voltage, you're going to get more amps actually going through, and vice versa between there. With water, we could measure the volume of flow through some other kind of device, so how much is actually gone through a period. With electricity, we measure the amount of charge that's flowing with a circuit over a period of time from 2 points, and that's expressed as amps. So you have to remember, talk about voltage, battery source, tank, how much pressure and potential energy it could actually have, versus amps is measuring the actual flow within the current once you have it going on. So is it slower or faster than what's going on? And if it goes too fast, things could go wrong, or if it's too slow, things would also not work properly. So if we go back to the water tank kind of analogy in the beginning, because there's always a direct connection between voltage and current and amps. Let's say that we have 2 tanks, each with a hose coming out of the actual bottom. Each tank has the same exact amount of water, but the hose on one tank is narrower than the hose on the other one. So you have to think, it's like we have 2 batteries of the actual same voltage, but how things actually can start flowing through it. So the actual hoses and that flow you're going here. So if we're thinking about wires or things like that. We measure the same amount of pressure at the end of either hose, but when the water begins to flow, one will flow at a faster rate. So the idea is like, well, okay, we have the hoses, we have the tanks, we can get the same amount of pressure measuring that, so which would be your volts, but the rate at which the water comes out would be different. And so you know this, like you've done anything for like water guns or anything or hoses, that, you know, large opening, the water's going to come out flow, but the narrower you get it with that same amount of pressure, it's going to start becoming a pinpoint and have more energy and flow faster from it. So the flow rate of the water tank from the narrow hose will be less than the flow rate from the water tank with the wider hose. And so how much you get coming out of that from here, and then what you can actually do with it. So in electrical terms, the current through the narrow hose is less than the current through the wider hose. If we want the flow to be the same through both hoses, we have to increase the amount of water or charge in the tank with the narrow hose. This increase in the pressure, so the voltage, at the end of the narrow hose, pushing more water through the tank. And this is announced to increase in voltage that causes an increase in the actual current. So these are bigger things, but just to remember again, well, we need to worry about volts on the amount of energy and pressure that we actually have. And we have to worry about what's the actual flow that's going through there being the actual amps. And we need to worry about the actual levels depending upon what components we put in place. So again, too high, we could blow stuff up. Too low, nothing's going to happen. If we put a lot of components on the actual circuit, well, we're going to start having other problems. And we have to worry about how much power do we need to actually power this device, and then how long would that power actually last. Now, we won't go crazy to that in this course. You just have to worry about that when you're building circuits. You have to worry about that. Well, how much power? What are you going to do? And then you have to worry about the physical, where you're going to place it, depending upon the entire structure that you're actually building itself. So now we're starting to see the relation between voltage and current, but there is a third factor to be considered, and it's the width of the actual hoses themselves. This means that we need to add another term to our model, or this water tank analogy. So water being charge, pressure being like voltage or volts, flow being current, and the hose width now being resistance. Is like, well, how much then is the flow being restricted or not restricted? Because we may get the right, say, voltage and amps, so the right battery source, so we get the right flow, but maybe some components along the lines can't handle that flow, like, that LED where they showed in the video and it burst. Well, then you need to restrict that. So, you restrict it by squeezing the hose or something like that. But so we want an analogy of like some material that'll take those electrons and slow the flow of them, so lower the actual amps to a level that the device can work properly, or the component that you're connected to. So again, considering the analogy of the two water tanks, one with a narrower pipe and one with a wider pipe, it stands to reason that we can fit as much volume through a narrow pipe so it fits as much volume through a wider one at the same pressure. This is resistance. The narrow pipe resists the flow of water through it, even though the water is at the same pressure within the actual tanks. So it's like the volume and what you're moving, it's just basically slowing it down as part of the analogy. We have to worry about that resistance. Now, in this course, you don't have to start freaking out yet of like, well, how do I know what resistance to use? Well, that goes into further things, into other electronics courses and things you can dig deeper by some of the other books and things that I provide if you need. The stuff we'll be building is generally they tell you, like, well, with this LED, use at least this level of resistance, or these components, they will tell you through diagrams. I'll be talking about later what you need to follow. And then you just need to know, well, if I'm going to start hooking things together at this basic point for this course, okay, well, what do I need to set up first, and then how can I combine it after that point? So what's that basic little circuit, and then how can I add more to that actual circuit and build off of that point? So in electrical terms, again, when it comes to resistance, this represents by two circuits with equal voltage but different resistance. The circuit with the higher resistance will allow less charge to flow, meaning the circuit with the higher resistance has less current flowing through it. So again, we can have the same voltage, so the same battery source and pressure that's applying, but then the amps that's happened, so before to roughly after. So it basically slows everything actually down, and since this is a closed thing, it slows the whole actual system down. So again, but we also have to worry, too high of resistance, it's going to slow everything down even more. So even things like motors and other devices is that we'll have things later on called resistors that we'll talk about, that actually material that slows it down. But some of these other components that we use, if they're combined together, they also create some kind of resistance or stopping within there as well. And we need to worry about that. So how many things we connect. This isn't going to be just like general software development where you just keep throwing stuff at it and it's going to be okay. We're dealing with like physical realities. So again, looking at this overall water analogy again in this flow, so the liquid itself being like the electrons flowing, you have pipes which represent material, conductive material allowed to flow. You have water tanks like up here that allow the actual voltage, so your battery actual sources. You have this circuit, which is this whole path from a higher pressure to a lower pressure and coming back, and you have components in between that are being used, that's using some of this flow to do some work, and you have things like the valves here being resistance to restrict the actual flow. And so if you're thinking like, okay, well, if we were here, we have a tank full of water, we start pumping, which creates pressure to move through here, wants to leave and come back to the actual tank. Is like, well, it's going to flow through these material, slow down by anything that's happening here in the resistor, hit this actual wheel and causing it to actually do a move, but which will slow down the water some, and it comes back to the circuit and keeps going. Can be other problems right here. So if we have too much pressure all of a sudden, we could get, okay, these pipes bursting that's coming out. If we completely close this, nothing is going to actually flow. When it's coming through here, if we don't have any resistance and we have a lot of pressure that's coming through here, so voltage, and then the flow is really fast, so a lot of amps, when it hits this, it could burn this out, so maybe that whole wheel just gets destroyed to motors. So again, we can't just randomly connect things together and think that it'll be okay and test stuff. Something's going to happen and could blow up. And like the simulators, it'll be okay when you do that. Physical things, you're like, well, now you got to buy a new component. That's it. And you have to worry about that. And sometimes that can be fun, but you also have to be careful because like the levels that we're working in this course, we're okay not to get harmed. But if it goes large enough, like it could harm us. And it's the fact, well, things exploding, but then also the fact that we're conductive, and so if you get enough amps going across your actual heart itself, it'll stop it. Or your muscles themselves are seizing up, and you could have damage to yourself. So you need to be careful that you're working with most things, being careful about what you're touching. Now, the devices we'll deal with are basic, but for other electronics, you want to be careful what you do and not just randomly touch it and the damage you could do to yourself. So now going from that water analogy and going back to like a circuit and say if we took apart like a handheld fan, well, it's similar that again we have like a battery here, say it's 9 volt, and we could look up and knowing, well, we know how many volts, we know what pressure levels that it will actually get, and we get the actual flow, which generally will go from higher to lower, which we'll talk about when we add more in terms later on, but going from positive roughly to negative, we can think about here. You have something, components that's along that line, say this motor, this fan, that is actually using up for some of it. We have a button here which then allows for starting and stopping the actual flow at all, and switches and maybe changing the actual circuits. But we have the same kind of analogy when we connect everything together. And we need to know this to pick the right power sources. We need to know this that, well, if something's missing from this entire cycle, what could be going wrong to fix the entire circuit, and what do we need? Now, another term to keep in mind is we've talked about conductive material so far, so that's like atoms, like material that basically allows the free flow of electrons easier, and different materials have different levels of conductivity you want to work with. But we also want to be careful like to use insulators, and like an insulator is a material which is poor conductor of electricity or heat. Things like wood, glass, porcelain, styrofoam, high enough levels, lots of stuff will still get destroyed. But for our basic level, okay, well, we need to worry about that, because if we just have exposed metal, metal touching metal then will allow the flow of electrons. When it's not touching, you go through air, you're okay. If you get high enough, even the atoms that are in the air will allow the flow of electricity, which causes problems. But for us, we are fine. That's why even looking, say, to the left, we see some components that you're going to see these wires that can always have plastic coatings. Even this resistor in the middle is plastic. Is like, well, all of these allow for that flow. That, well, inside of the wire here is some metal that's conductive, but the insulator on the outside helps that if two things are touching, where there's no problem. But say things like these resistors, this metal that you can see coming out here, well, that's something you have to be careful about, because you touching that or the two resistors touching is going to cause what's called a short circuit that we'll talk about later coming up, and change that flow of electrons. So what is a circuit in general? Like, what do we need? We know we have electricity. We know we have volts being that pressure we need to push electrons through. We know we have current and amps being the actual flow of it. We have conductive material. We have insulating material. Well, then what's a circuit overall? And which is something we need to really take advantage of everything that we've been talking about. So an electrical circuit is composed of individual electronic components such as resistors, transistors, capacitors, blah, 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 connected by conductive wires or traces through which electricity current can move. So you'll have wires, or you'll have, like you can see in this diagram, you have wires here. You can even see here you have these lines that are under here, which is conductive metal, which then is coated with some kind of insulator on top, which allows for that flow and movement of electrons in some kind of path that we set. And so we need to set that. And there's other properties of being it has to go from a beginning point of positive to negative and be a complete cycle that you're working with. So a battery or a wall outlet has a certain number of volts. So we know that, the pressure you're actually dealing with. All these volts are sitting there waiting for us to use them. But there's a catch. In order for electricity to do any work, it needs to be able to move. So it may sit there in the battery, but until something connects with it that allows for that flow, nothing is going to actually happen. And so that sometimes batteries, you're being careful. While they're stored in plastic, they're stopping the actual movement of those electrons, as long as it's not high enough levels. But then you connect it to some kind of conductive, so touching, but completing and making a cycle or circle where it can go from that higher to lower pressure. Well, then you have that movement of electrons, which then can be taken advantage of. So it's kind of like blowing up a balloon. If you pinch it off, there is air that's inside of it, and if we release it, until we release it, nothing will happen. But it won't actually do anything at the time. Like, we can take a balloon, we blow it up, we have the pressure that's built up within that balloon, we can hold off the actual end of it, and until we release it, nothing is going to actually end up happening. And so this is an analogy then thinking for a battery source as well. Analogy being, okay, connecting it to conductive material and completing a circuit to allow for the release of those actual electrons, and then it can start doing things. So electricity can only flow through material that conduct electricity, such as copper wire and other things, as long as depending on how much pressure you actually have. If you connect a wire to a battery or a wall outlet, and don't do this on your own, don't practice with this. Like basic batteries, it may be small, but don't plug in. Like just don't shove a fork into an outlet, please. But if we do this, like if you're the metal, like the voltage in the wall outlet is discharged. So like when you complete that complete circuit, is that even your skin touching stuff, if you're taking that metal fork, that you could end up completing an actual circuit and cause problems. This is things like electric fences. You'll see people touch them and sometimes won't have an effect, but then they're like, oh, they have rubber shoes on. And again, their body is being this conductive, being like material and they're touching it, but the shoes stops the flow of going to the actual ground. But if you took your shoes off, and even your socks, you touch the electric fence, it's going to flow from the fence into you, through you, and then into the actual ground, which will also completing that actual circuit, and thus causes massive problems. But if the wire isn't connected to anything else, the electricity won't have anywhere else to go until like you move. So that's why we have the battery source in the beginning, and when you connect everything, and if we don't connect it, it's going to stop the flow. If we connect it, it's going to allow the flow. And we can take advantage, like we know we need to have that. If nothing's happening, we have to worry about, okay, is there a break in the circuit? Is something going wrong? Or maybe we purposefully introduce a thing called a switch, which then breaks a circuit and stops the flow and stops it doing any work. So like turning off a light switch itself. So what makes electricity move? So electricity wants to flow from a higher voltage to a lower voltage, that overall pressure. Just because we have it within there, and we say water within something, but there's a lot of pressure, it wants to actually move. This is exactly like the balloon, going back to that actual analogy, is that the pressurized air in the balloon wants to flow from inside the balloon, so the higher pressure, boom, to the outside of being lower pressure. So when you release it, it lets it out. And this is the same thing then when it comes to electricity. So if you create a conductive path between a higher voltage and a lower voltage, electricity will flow. You'll get that current in those amps. And if you insert something useful into that path, like an LED, well, then it's going to light up, and you have that whole overall circuit. So the question now is to know, well, how do you know when you're connecting to a power source, how from the higher and lower side? How do I know to connect everything together? So where do you find that higher voltage and lower voltage? Well, something to know, like every source of electricity has two sides that we're dealing with. You can see these on batteries, which can be the metal caps and both ends, the positive and negative ends. 9-volt batteries is the different connectors. So, the bottom and top of batteries, these 9-volt square ones, you have different posts that are shaped different ways that are designed to actually connect, and they're just markers to make clear what's the positive and negative. So you always have to check for your power source, which side is the positive, which side is the actual negative. In batteries and other direct current flow kind of circuits, voltage, these are referred to as the terminals of either being positive, so the plus, and negative. So I think a lot of us, when we're used to putting batteries in, you put in devices before, they tell you which direction you need to actually put them and how to place them. And if you don't do it right, circuit doesn't work. So you need to place them properly so that we're getting the start of one part of the circuit to be with the positive and the negative, and that flow going from one to the actual other. So building up again from what is a circuit? So why does every source of electricity have two sides? This goes back to the idea of that potential or that pressure, and that you need a voltage difference in order for electricity to flow. So that's that voltage and that pressure we had overall. It sounds silly, but you can't have a difference between two things without having a difference. So you have those two poles, you have the stored energy with whatever battery source, whatever is being used to build up that pressure or potential, but basically for your electrical source, so the type of battery, whatever else, lithium, polymer, whatever. And you have to have that potential that it wants to move between it, and until you complete that actual circuit, nothing's happening yet until it connects together. So in any power supply, the positive side will have a higher voltage than the negative side, which is exactly what we want. In fact, when we measure voltage, we can usually say the negative side is 0 volts, and the positive is however many volts you have stored within the battery. So 1.5 volt battery to a 9 volt battery, or whatever other power source you're actually working with. So electric sources are like the pumps. Pumps always have two sides. An outlet that blows something out, and an inlet that sucks something in for an actual pump. That's why we're thinking about this analogy for right here is that pressure of the pump going down, taking whatever reservoir we have here, moving the water through, and then at the same time sucking something back up, and that's due to the higher and lower actual pressure. So batteries and generators, things that make energy, and solar panels work the same way. And so something inside them is hard at work moving electricity towards the outlet, the positive side, but all that electricity leaving the device creates a void, which means that the negative side needs to pull electricity to replace it. So that's where you're getting that pull out and going back in, the electrons flowing through their components, and our components doing work for us, and everything coming together for your actual robot and the internals for us. So what have we learned so far as a quick recap? Again, voltage is potential, but electricity needs to flow to do anything useful. Electricity needs a path to flow through, which must be an electrical conductor such as copper wire. Electricity will flow from a higher to lower voltage point, so from positive to negative. We can know the general terms in here. And DC voltage sources always have two sides, so being the negative and positive side. And so making sure you hook those up properly. If you don't, it's another source of actual problems. So, continue on with this. We think, well, let's start with a simple circuit. So that flow where we need a battery source, we need connective material between it, we need some components to do that. And so we're finally ready to start doing some work. So if we connect the positive side of a voltage source through something that does some work, such as a light-emitting diode, and back to the negative side of the voltage source, electricity or current will flow, and we can put things in the path that do useful stuff for us. And so in this case, you can see an example of the drawing would be a resistor to stop the flow so that current, lower the amps, it's going to go through the light-emitting diode, and the flow of electrons through there then allow for light to be emitted and maybe small amounts of actual heat, and it comes back to the actual battery. Now, so here, as long as these are all connected and we have this flow, this light will be on until this battery is exhausted. We have no more power. And there's always some loss of actual electricity through other forms. The electrons itself being lost here, being used up with the resistance being transformed into something like heat or other sources of energy and going back, but it'll stay on continuously through the cycle. We cut or disconnect this wire, that light will turn off because we're stopping that actual flow going through everything. So the circuit path, which is always required to get electricity to flow and do something useful, is called that circuit. That's our circuit. Is that from that one side of our energy source back to the energy source, this cycle, and then the components that we have connected in between. And then we can have things that are called like series or parallel where it branches off, so, like even like a river or hose that's branching off. And you can see the issues if you don't have enough pressure, what's going to happen overall between all of that. So same analogy. So a circuit is a path that starts at some place and which ends up exactly back at the same case of being some actual like ending point. And so these are basic circuits. And so when we start building stuff up for our entire robot, we're going to have a whole bunch of different circuits that then all reconnect back together. They may be sharing a common power source, but they're separate circuits. They're all drawing their actual energy and doing more work. So all of our sensors, effectors, actuators all have electronic components that all need this electricity to actually do their work. We get this flow coming back into the actual controller, which itself also needs this power to do its work, and then keeps building up. And so we go from these very simple circuits to more complex circuits that are doing work for us. Now, other terms we need to worry about here is things like load. And so the reason we want to build circuits is to make electricity do useful things for us. The way we do this is by putting things along that actual circuit that use that current or flow up and that make noise and run or do whatever, so buzzers. So we can put it in there, but we have to realize, again, the more things you put in there, it's going to eat up, you could think of it analogy-wise, some of that actual flow and slow it down. And so after a while with this load is that too high of a load, it's going to shut things down. It's not going to work properly. And so we have to worry about what pressure are we adding to this. If we add more pressure, can the actual wires handle that and not just burn out? And we have to be careful overall. So what is the amps that a wire can actually hold? What can handle for the circuits itself? What is your power source? Once we get all of that, how does everything fit into the physical components of that body, and what physics effects does that have? Like a placement of a battery and you're trying to move something, but it's so heavy it causes extra problems. So what do you do? So these things are called loads because they load down the power supply just like you're loaded down when you're carrying something. So really light, maybe fine. Put a lot of things, wears you down, more energy. The same way that you could be loaded down with too much weight, it's possible to load down a power supply too much will slow the current down and cause problems. And so especially for things like the controllers, if there's less power going to that, that's like less energy going to your brain. You're not thinking the best. Boom. So, but unlike you, it's also possible for a circuit to have too little. So two little things here. This may be like which let way too much current flow, meant running fast for everything else, and this could cause problems. So you want to learn with the rest of the circuit, we're hooking things up, but we can't just keep throwing things in. If we don't have the right actual pressure and amps, problems could happen, things exploding or things just not running because there's not enough actual power. And especially when batteries die out, what happens? Now, another term and things to be careful about is then short circuit. So if we have a circuit, and again, that everything wants to flow from higher to lower, but it also wants to take the shortest possible path. And so, example here, like from the circuit, is like, don't do this, but if you to connect a wire directly from the positive end to the actual, so from the positive to the negative, it's going to instantly start flowing. And maybe if it's a small enough battery source, you'll be okay, but it's going to keep just instantly flowing. Generally, this will be like uncontrolled speed, so you'll start feeling heat because it's going, and the pressure that's coming from here is you'll have some heat coming off of it, and this could cause problems of things exploding, everything else. So when you have a battery source, be careful to not connect that. Lower ones will be okay, but higher ones, you get damage you're not going to come back from. And this is also then when you're creating the circuits, is that when you're connecting things together, if you have a circuit and you have a path and two pieces of metal are touching at all, that will allow the flow of electricity. And even if they're really close, if it's high enough, those electrons will jump. Our circuits are going to be weak enough that that won't really happen. But if it is high enough, well, that'll jump, and you have to worry about that. So you usually want to have insulating material in between, because if anything starts touching, it's boom, instantaneous. That short circuit, things could blow up, your circuit's not working properly. And so you need to check for this and be careful. So even when you're touching things and it's on, that can also have problems. And if you've got this hooked on later on with the Arduino in your computer, you want to be careful what could go on. So, like, the idea of a short circuit in the fast, it seems like could be the best possible circuit, but you have to remember, like, there's problems. That electricity current wants to flow from a higher voltage to lower, and if you put a load into the current, you can do something useful with it. If you do have a load in the current flow through the circuit will be limited to that which your device consumes, which is usually a very small amount. However, if you don't put anything into the resistance flow, there won't be anything else to slow that down, and could be considered being infinite. And so you have that path and everything else, and so even in this example, it's just going to take some of this from here, and it's going to keep going this way and not get as much power from this way, or the whole overall circuit just won't work properly. Your power supply can't provide infinite current, but it will provide as much as it possibly can. This could cause your wire to burn up, damage the power supply, drain your battery, or other exciting things, sparks, like you don't know. Most of the time, your power supply will have some sort of safety mechanism built into it to limit the maximum current that's coming to be okay, but you still want to be careful. So the bottom line, if you notice that things are suddenly becoming hot or a part suddenly burns out, immediately turn off the power source. Now, all circuits and everything are going to generate some kind of heat. You're used to those TVs, everything else you feel after a while. If it's been running for too long, it has some kind of heat. So you have a certain level, but if you're not sure and it's getting too warm, you touch it, and oh, that's burning, and you pull back from it, unplug it from the actual power. If something blows up, it could be a small thing or even a puff of smoke, or if anyone has actually smelt burnt electricity, you'll know that metallic-y, smoky smell. You want to stop and you want to unplug it and you want to be careful. If you're going to go and touch anything, then having something that's insulator can help you. Now, for our circuits and everything we do in this course is very basic, but I don't control everything that you guys are doing at home, so you want to be careful with what you're working with. Now, another term is an open circuit. So it's the opposite of short circuit is an open circuit. This is a circuit where the loop isn't fully connected, and therefore there's no circuit at all. You have no flow. So remember, you need to have that complete flow and that pressure from the positive to the negative and the flow of electrons for things to actually be moving. And if anything interrupts that flow or separation, so two pieces of conductive material not touching at all, well, then your circuit stops running. So that could be useful if you have a switch and you want to shut things off, or maybe it's something that's wrong as there's a broken wire or something else, or we haven't connected something properly. So we have to check, okay, are we getting that right flow going back? So unlike the short circuit above, nothing will get hurt by the circuit, but your circuit just won't work. If you're new at circuits, it can often be hard to find where the break is, especially if you're using breadboards, we'll talk about later, where everything's hidden. So you just want to be careful, because even in wires, like we could be working with a wire, it looks fine to you, but internally there could be a snap or it could be broken and it's not working. So when you start building stuff for your robots, you have to worry about not just, well, what's going on in my code, but what's happening with the physical actual components themselves, and maybe something's wrong with the wires and not your coding at all. Or if your robot's moving at all, what's happened over time? Has something come loose? Has something broken? Is that a reason why it's shut down? And maybe you should redesign other things so that doesn't shake or move or disconnect, and you want to keep that circuit going. So if your circuit doesn't work, the most likely cause is an open circuit. So if you know your power source is fine, you have energy in the actual battery, everything else should be okay, and it's not working, well, then it means, well, you don't have something connected up properly. And that's one first stage. Or maybe you have too much resistance or so forth. So this is usually due to broken connections, loose wire, short circuits, dealing with stuff. All these things can cause problems. So there we go. There's a lot within here. This is why you can have entire courses on electricity. We still have more to go for this lecture. But you have those terms of that circuit you're going through. You have load on that actual circuit. You have short circuit that could be problems and things you want to be careful about. And you have open circuits, which you could design in if you want that. But then if you know, well, this should be running, well, maybe there's something wrong. There's a break, or you have an open in your actual circuit. But now we're going to start transitioning into, say, some components and things to do our work. Because really, we just need to connect things together. We just need material to touch. And one tool that we're going to be using is connect everything together is a breadboard. And so if you got the kits, you'll see these. If you're working with the simulator, there's also a breadboard within there. And it's a common thing for just building and quickly prototyping circuits. Because in the end, you'd really just connect everything together yourself. But you don't want to do that all the time because you have to disconnect in the time it takes. So you'd rather have a quick little tool so that you can create paths and know how to read and connect everything together to build your circuit, test it, and then once you have it right, physically build it after that point in time. So that's where we come to these things called breadboards. You can see here. Generally, so there'll always be some kind of insulating material on the outside, a whole bunch of different holes, and then conductive material inside that's connected together in different ways. And as long as you know how to read and know the flow of electrons between where you plug in to where you know it's going to come out, you can start building things. So electrical breadboard is actually referring to a solderless breadboard, and it's great use for doing these temporary kind of connections. And what you get more inside of them is that you get that insulating kind of plastic material on the outside, and you have a whole bunch of little holes that are inside of it, but inside of it you have this kind of clips like this, these little metal. And the idea is in that hole you'll plug in an actual wire, and this clip here will hold it. But then all of this is metal and all connected together, so to allow the flow of electrons through the actual circuit. So wherever they are, it's this entire line. And so what's important about that is when you see things again here, go back to here, is this breadboard here, is that you'll see these little lines and you think, okay, it looks really weird, but I have all these little holes, and you want to hear that that's where you're going to be plugging in. Here is the actual wires, talking together, and then you just have to know, okay, well, how will they flow? And there's always common rules, and you kind of see it from here, is that this row that we see here, so we can see that it says 1, and we have A, B, C, D, E, as well this row right to here of this 1, 2, 3, 4, 5, these are all connected together. So if I plug in one thing up here, and then plug another thing here, the electrons will flow in to here, through here, and then out through whatever else is connected from there. This side over here is separated, connected separately. This little gap in between is called the IC or your chip. It's space enough that you can have a chip in between, but they're separated between this. And generally you'll see things here where it's positive and negative. And what this is that this entire line, so where you see positive, this entire line going down out here is all connected together. And this line going down here is also connected together. And so sometimes when you want to hook up power and we have a bunch of different circuits, we don't want to have to put a whole bunch of wires from the power source into over here. We want somewhere to share it. And so we would connect the positive side to one spot right here. And then that allows then that anything that plugs in down this row and comes into over here is like, well, it's the positive from the positive and going over. We can then connect the negative terminal to this and then have the circuits going back that we need to complete that at some point in time. So going from the positive or negative. And this is for circuitry we're dealing here. Later on, we're going to have the Adrenos, and the Adreno handles some of the power and negative there as well. So you can really connect whatever wires you want, but it's a good convention that if you have your power source, you'll connect it to the line that's marked negative. For your power source here, you'll connect it to positive. These lines, maybe you'll have lines that run over to share to each other side, and then you start connecting things together. And that's just so that you're like, okay, I know that I'm using this for negative, I'm using this for positive, it's marked, and then everything else becomes clear after that. So again, if we have a circuit that's going from here to here, now if I connect a line from here down to here, let's say, well then we're completing the circuit of whatever's connected here will flow from here down to here. If we go from the positive, say up to here, through here, down here, and then back to the negative, we'll get that kind of flow. And don't worry, as later on I'll be demoing some of these things live. If this is just the first part of knowing what the breadboard. So I'll be doing stuff in the simulator to show this, and then I'll be doing stuff in physical to show putting the actual wires in. And that'll be coming in other videos. Now, other key terminology building up that we have to get used to, and you'll see within the books, is things like getting schematic diagrams. So a schematic diagram is a picture that represents the components or processor devices and how they're all connected together. So you guys are used to this from other courses. So things say like the transit map for Calgary, you have symbols and how they're connected. And then you also have things like this one here at the bottom, which is an example of a circuit diagram. It doesn't always mean that this is how physically things are located, but it shows, well, the path and flow of where it is. And we're not really going to be designing as much of our own circuits this lower part, but when we be given circuits, we have to know, okay, this is how it says from the book to connect it up, so I need to connect it up that same way. And then if I know how to modify that circuit by just making different connections, I know how to connect everything together. So a circuit diagram or electric schematic diagram, like there's all these different terms for it, is a simplified conventional graphical representation of an electrical circuit. So it's the arrangement of the components, the interconnections, the diagram, so from your power sources and everything else that you are working with. So, and there's different symbols. And so I'm going to be introducing some of these, and they're good to learn. It's not that bad to remember some of them. You don't need to go super crazy with it. But you get things like the power source saying the positive, and you have the negative side. You know, these lines that are drawn out here are showing the connections. The jump over here means, well, these two lines aren't connected, whereas the dot here means, yeah, these are connected. You get like zigzag lines for resistors and things like diodes. And don't worry, I go through the components, we have diagrams there, but you just need to know that, well, how do I read these? And going from this, because the booklet that comes with the kit that we have shows some of these. Maybe you'll find them online. You'll also find things that are called like wiring diagrams that don't follow this, but they show more of the physical wires, and you kind of use both to learn how to build and put the circuits together. So another example is one like this one here. So you get the lines coming from here, but this is a case one where it incorporates things from the actual Arduino that we're going to talk about later, where it says, okay, well, what pin do you put it in? You have this line connector, you have things like an LED, you have a resistor and a power source that's coming through. And it doesn't say where they're physically located, or the length of wires or anything else. It just says, well, one to the next to the next. So in some way, we need to go from that pin to then the actual diode, and then to the resistor, then to the power source. Boom. Other things we're going to be using, wires. We're used to it. You're going to need wires because that's part of what we're using to connect things together, say, especially for our basic circuits. If you were designing stuff yourself in the future, you may prototype and just use the wires, use some wires to connect. Other ones will be actual circuit boards that actually have metal, like thin layers of metal that are separated from each other to allow for that actual flow. So the wires is like in a circuit, carry the electricity from the current or certain source of your battery sources to other components, and vice versa, connecting back and forth. They all contain a conductive core surrounded by some kind of insulated material. From here, so you can kind of see these here, that you can see the plasticky outside from it. You have these ends that are exposed, but throughout this then is the actual metal itself, usually little strands of wires to allow for easily bending. You then can't touch plastic to plastic in these cases to get to conduct. You have to get at some of the metal from the end, so maybe you need to take off some of the plastic to expose the metal, and you have little bits, but this is what then you touch to another wire to make connection or something else. So all these here. Now, the color of the wires doesn't really mean much other than to help you organize things, that you can follow from one path to the next. And so you'll start picking what colors you want to make it easier. You can pick randomly in the beginning, but it'd be nice if you follow conventions. You don't have like a red wire next to a red wire next to a red wire. It's nice if you change up the colors, especially for wires that are right next to each other, because it's easier for your eye to actually flow and see where things are going on. And one convention, like, you do whatever you want, but like one convention for North America is generally to use wires that are red for indicating that this is connected to the positive end of the power source, and ones that are black to say that's connected to the negative. So coming off of the power source, you'll see those. But just because you see a black and red wire in other circuits that other people do online, it's not a guarantee, but it's a good convention, and I like to stick with that convention. Because things get chaotic. Like, this is an example of tons of things plugged into an actual breadboard for circuits. And like, the more complex you get for circuits, this can start happening, especially prototyping. We'll start with simple, but you build it up. So having at least colors can make it easier that, okay, look at these ones that are next to each other and everything else that's actually flowing. And maybe you only use red when you're connecting power to different components. But again, we have a limited number of wires in the actual kit itself. So that's the point of connecting everything together. And so even though the schematics are going to look nice, most times when you put them together, they're not going to look so nice. Like, maybe you'll make nice flows, but you have to realize, as long as you're getting from this point, plugged in a breadboard, it's going to flow through here, down to this point, and then it's going to flow through this line. So this says to say this pin here, and then out, and so forth. Now, in your kits and everything for breadboards, is that those wires in standard are hard to plug into stuff. They're good if you're twisting together and you're doing soldering to make them permanently stick together and allow for nice flow of electrons doing other work. But most times for the quick prototyping, you want to be able to quickly, easily plug stuff in, and the stranded wires don't work. So what we get instead is called the jumper wires, and you'll see those in the actual physical kits themselves. So they look like this. They're the wires, they're colored, they have the branded metal, they have these plastic bits here with metal exposed, and this metal here is not stranded, it's kind of a little bit more firm. And so these are wires designed to connect different components on an actual circuit itself. And you have different ends, basically. One that's a pin end that's coming out, that's coming here, or it could have a slot that allows things to plug into it if you need for components, but just allows for that flow and connection, easily connecting things together. And so when you're looking at your jumper wires, you'll generally get roughly these three combinations you're working with. So you'll get pin to pin. So it's one where there's two pins coming out. So you're just connecting from one component to another. So into the breadboard to another spot on the actual breadboard. You'll get ones that allow to connect things in between. So maybe for these jumpers, you're just connecting like two components, say an LED or something differently, and you want to plug one end in and then plug into something else. Or you get connectors like one is the slot and one's got the actual pin, and so you'll see where one end can plug into the board and the other end something can be plugged into it. It depends upon what you're working with and how you set things up and trying to make that metal to metal conductive connection. But you have to worry about these wires and you're working with them, be careful bending it, because like this is fine, but you go too hard here, it's going to snap something internally here, and you may not see it, but well, this hard piece of metal is connected to the branded metal that's inside here, and so if that breaks, we're getting an open circuit and it's not working. So it may physically look like you've plugged it in properly, but internally something could have actually been broken. Woo! Lots of fun there. So the wires again. So overall, you can see, boom, this chaoticness, which can happen because when you're coming with the kits, so you'll have some longer wires to shorter wires, and too long of wires can cause issues for robotics projects, but for our basic ones, it's not going to cause a bigger problem for right now. But when we get to more complex circuits, we have to worry about the layout, and we get these breadboards, you're going to get a lot of these kinds of things happening with the physical kind of actual components. But you still have that circuit, you still have that power source, you have that current flow of amps, you have that voltage being the actual pressure. Now, we've talked about all these ideas. We talked about resistance. We talked about the fact we have these metal wires conducting. That is physical material. So some of the other components and things you're adding on, well, you have to worry about those as well. And I'm just going to introduce you to a few of them. And you're going to see them in the kits, or you're going to see in the simulator. We need to drag and drop them. And I've talked about you have resistance in a circuit. And resistance can be anything that's restricting the actual flow and that's going through materials. So the wires themselves have some level of resistance. Lights and other things will have some level of resistance. They'll slow it down. But then you also have where if you're trying to specifically go from one level of flow, so one level of amps, to a lower level, you then have resistors. And so a resistor is a component that resists the flow of the actual current, and it's one of the most basic components. And so the idea is they're all different sizes and everything else from this, but it just means that there's some material that's in it that you have a conductive wire on one end, you usually have conductive on the other end, and then whatever material that's inside there slows the flow of electrons to a specific amount, usually controlled measurement that you're actually working with. Now, a nice thing about resistors is it doesn't matter what direction, so it doesn't matter. You don't have to worry about orientating them as far as that, whereas you used to put them in from one side to the other side and it stops that actual flow, because other components you have to worry about how do you orientate them, because you can't just willy-nilly put them anywhere. You need to put them in a specific way. So this is one example, and you have resistors down here at the bottom. You can see generally the ones we're working with, you can see in the kits that have this longer leads on the end, as they're called for metal, they're all conductive, and the actual resistive material in the actual center itself. The symbol for a, again, circuit diagram is this line is this zigzag with an R. Most times will actually indicate what level of resistance they're actually providing themselves. And you get different sizes of them. We'll go through that and all these different things. Now, themselves, when it comes to electricity, like when you're looking at the ones we're working with, they're going to be this a little bit larger. You're going to see these bands that are on them, and then there's a certain way to read these to figure out, well, what is the actual resistance of them? Because when we're talking about resistance, it's measured in ohms. Because we know we have voltage to remember that pressure, we have amps as a measurement unit for the actual flow, and then we have ohms to talk about that resistance of actual flow for the material, so how much will it actually resist it. And so when you're working resistors, in the kits, they'll probably mark them on the sides, but if you're not sure, you don't need to go through this chart. There's a way that you go through calculating this to figure it out, but it's based upon the color of these codes here. And if you're not sure, you can always just Google, like resistor converter, and there's usually programs where you can just list the color and it tells you what's the actual ohms to use. And you want to be careful, because you could plug a resistor in, and if it's too high, it's gonna like, hey, the light's really dim, and it's gonna cause problems, and it's not what we wanted. Or if it's too low and it doesn't restrict current level, we could have problems on the other side for the circuit. So you want to follow with roughly the resistance. Most of the kits and stuff will tell you, here's the bands and the colors, what it looks like. Or if you've taken them all out, you're not sure, you have to go back and look at these on the orientation from one side to the other, so the gold band on one, reading from here downwards, and list those, and then you can figure out the proper ohms. But sometimes the kits, it's hard to read those colors, fun of everything else. Other resistors, when you're looking at stuff, it's not just these components, because if you're looking at anything like circuitry, like this one up here, we see components. We can see these lines down here, which is the equivalent of the wires. They're coated on top with some kind of like insulating material, but allows the flow. But you can see right here, we have resistors. We have other components. They're called like capacitors. These are your chips. But right here, we have a bunch of resistors that we're used to. But you also get really tiny little resistors here that you'll see on actual devices when you look at them. Usually with the ohms or the things listed in here. Or we get things like this one here, which is a photo reactive resistor, which means it allows electrons through, but depending upon the amount of light that's physically hitting this, it'll change resistance, which is interesting, because you could use these then to do stuff in circuitry, like very, very cheap and shitty light sensors to make things react. So sometimes if you look at those robotic kits, sometimes they'll have these on as like little bug-looking eyes, and it says it follows light, and the idea is they'll place them in different sides, and you take two readings to know what's the resistance here, what's the resistance here, know, well, which side has the most kind of light, and where do I move to get to that location. So your beginning level of a shitty like sensor. But otherwise, the rest of circuits, you need these. So we're not going to be working with any of these. If your kit comes with one of these, or in the simulator, we can work with the light one, but generally they'll look like this when we're working. They're easier for us to actually handle. Now, another thing we're dealing with is diodes. So a diode is a device that lets current only flow in one direction, so that current in the lines can flow either way when you have the motors, because there's the direct current, but if something happens, it could flow a different way. Like a motor moving could change a direct current into alternating, or cause problems to flow the wrong way, and flowing the wrong way can cause things. And so when you get diodes, they only allow that flow will go one way. So if it's coming this way, it'll go, but if it comes the other way, it stops anything happening. So it's kind of restrictive. It's like one-way valve for water flowing that only allows to go through this and will not allow it to come back the way usually used for the safety kind of mechanisms. Very important about this then is to know, well, diodes have two terminals being the anode and cathode, and the idea is that it's only going to flow from the anode to the actual cathode. And so you, like resistors, you can place either way, you can turn them around, but diodes, you have to make sure that you have them orientated properly, otherwise they won't work. It won't do what you actually need them. And so that's why in a schematic diagram, that's why they always show the arrow right here. It's a line coming in, the circuit coming out, and it shows the arrow to say the flow of electrons and the line here to say the block coming back. So your anode, you want to make sure you're connecting it properly. If you're looking at them, you may have them in the kits, but the other ways, they're usually guided by the same thing as like, well, okay, this side here, where if it's not close to the actual line, that's the anode, and this is the actual cathode, and I place it this way in the circuit that it tells me, following from the schematic diagram, that it's going from the anode from whatever line to the cathode coming out. But if you go backwards, you're going to have problems. And where this is really important for us in the beginning is then light-emitting diodes, because so our LEDs are diodes, and in a diagram, they're only really different because they add these extra lines to indicate that light's coming out of instead of normal diode. So when you have an LED and you put it into the actual circuit, if you don't connect, again, the right flow, the positive coming into the actual anode and then coming out to the actual cathode, it's not going to work properly. Basically, the light won't turn on. So when you're doing these circuits, you have to connect, do I have the wires right? Do I have the power right? And if I'm not seeing the actual light, well, maybe I need to flip it around, and then everything is good at that time. So we're almost at the end. Woo. Still more to go after this for the actual simulations and everything else, but bringing it back to like all these, we have 4 diagrams or pictures here, but they're all of the same thing, that we all have power sources throughout. You have power source, you have power source, and you have a power source here. So you have that voltage, you have that pressure that's built up, you have a circuit, so everything is connected together. You can see this from one side to the next, everything's connected through the breadboard and back. You have a flow once things are actually turned on from the power, so the actual amps that are going through it, and you have that diagrams, everything that's working on this. So if we work with one, well, this is a schematic diagram down here, and they're all the same coming down. So we know, okay, well, I've got the battery source, it's connecting out, it's going over to a resistor. From the resistor, it's going into the anode of the actual LED and coming out the actual cathode and going back to the actual negative. So let's say we got this light hooked up here. And when you work with LEDs, it's usually the length, or you can tell looking at them, the length of the actual wires themselves tells you which is the anode and which is the actual cathode. But if we come here for the power source, well, we see the same wire. We have a resistor. You can see it looks more. That's these two things the same. Connected over through the LED, coming back for that flow. If we go to the breadboard itself, we have the power. You know, okay, hey, look, we have red coming down here. So that means that all of these are connected to this. We have red flowing up here. We have black coming down here, so our negative side flowing throughout here. So we know so far the red's connecting to here. We know the black is connected to here. So remember, the flow for us, as far as we're concerned for this course, is going from that positive to negative. So it's going out to here, going down. Okay, there's nothing else connected along here, so this is, will short go through here. Here, these are all connected, so it's going from here into the breadboard, over into here again, the actual anode coming out the cathode, light coming out the LED, coming down here. You have the resistor is connected here, it's going to flow through here, and then it's going to flow down, back into the negative, over to here. So we get that complete cycle going through here. Boom. Blah. So all fun, all the same thing, but things that we need to worry about. And you can see now on this last slide, this is a very crash course beginning for the basics of electricity, currents, wires, and everything else. But I need to start from here from a basic introduction before we start going to more things about the adrenals and circuits and how they work, and then start worrying about sensors and actuators and effectors. And then once we understand more information around that, then how do we start doing more things in the controller and getting it to do work? So a quick summary, and there's way more beyond what's just on this slide that's throughout everything we hear, is again that electricity is the movement of electrons. Voltage is the difference in charge between 2 points, measured in volts, so your battery source. And you need that for the pressure to actually get things going. Current is the rate at which charge is flowing, so in amps. So the electrons, so the pressure of electrons, the electrons moving through everything. Resistance is the measured tendency to resist that actual flow in the ohms. An insulator is material that does not allow for the flow of electricity. A circuit is a closed loop that allows for the charge to move from one place to another, between from that positive, everything else to the actual pressure. Components in the circuit allow us to control and change things we're working with, and load is the amount of components we have on there. And all these things affect and come together, and you need to know this for these basic building blocks before we keep moving on. Okay. an hour and 31 minutes within there. So following after this, you should also then see some videos for one is demoing stuff using the Tinkercad simulator or whatever simulator is being used. From right here, so these kind of connections and playing around and kind of demoing some of this live. And then there'll also be another separate video which will go through another demo, but it'll start doing things with the physical components. Because some of you, some people have kits and some people won't. You're doing this, and a simulator is good enough to start with, but that's just a simulated program. There's some other things that happen with physical materials are not the same, and it's nice to also connect and work things together to get more of that embodied experiential learning of what you're actually doing. Okay. Other than that, like most of my videos, I want to end that I hope most of you are doing good. If you're not or having any issues, please reach out. If you just even need someone to talk to, reach out to a friend. Reach out to me or your teacher and just see what's going on. If there's someone you haven't heard from in a while, maybe you should reach out to them and just say, hey, how are you doing? And check in on them. Because everything in the world is difficult. And just even one glimmer of hope can help someone or help yourself. And even asking for help when you actually need it. Okay, other than that, on to the next videos and keep being wonderful people.